This is lecture 25 for Wednesday, the 1st of April. We're going to carry on with Faraday's law for this lecture. So we covered Faraday's law on Monday. Faraday's law states that the net induced potential in a current loop is the change in magnetic flux over the change in time. The negative sign in the equation implies that the induced field and the induced current oppose the changes in the field and current. If you didn't do it last time, you might like to check out the FET experiment. Just Google FET Faraday's law to experiment a little bit about Faraday's law and how that leads to a changing potential. So the first thing we'll do is an example that we didn't get to last time. This is a biological example. When you do an MRI, you're putting your body into a huge solenoid. They put currents through the solenoid, which changes the magnetic field of your body. So that changing magnetic field that you're lying in induces currents in your little muscle loops. So it's kind of an interesting question. If you're full of little conductive loops and you're sitting in a magnetic field, well, you're getting a bunch of currents created in your body. This question asks, how big are those current loops? So the first thing we can do is let's make a list of all the things we know in this problem. So the resistance of your muscle loop is about 4,800 ohms. It's not a superconductor. The resistance is pretty high, but it does still conduct. We're going to assume a typical change in magnetic field, that it goes from about 1.6 teslas to 0 teslas, and that doesn't take very long, about 0.3 seconds. Then we'll ask, what is the induced current as a result of this changing magnetic field? We'll start with writing down Faraday's law, which says that the induced potential, and we'll start with potential because that's something we can calculate from Faraday's law. After that, we'll go to Ohm's law and we'll calculate current from the potential. Faraday's law says that the induced potential is the negative of the rate of change of flux. So let's think, what are we supposed to do with that equation? D by dt means take a derivative, but we don't have a function. So how do we deal with change in flux over change in time? Well, if you think back to a beginning physics course, we know that velocity is the change in position over change in time, which means that to find the velocity, you do the derivative of the position function. However, sometimes you just have two different positions, an x final and an x initial, over a change in time. Then you say that v is delta x over delta t. We can do the same thing here with Faraday's law. You can say that your change as a function of time is just delta phi over delta t. And we have 2 points for phi, or we have 2 points for the magnetic field, so we can find the change in flux, and we know that the change in time is 0.3. So delta phi is final flux, take away initial flux. Multiply that negative through, so minus phi delta phi will give us phi initial take away phi final. Remember that flux is magnetic field times area. So we'll plug in B initial times area for our initial flux, B final times area for our final flux. If we ask what area is, we're saying that our muscle is a little current loop, so it's a circle. That makes the area pi r squared. So now we have all of our information and we can fill in our numbers. So our initial and final magnetic fields are 0 and 1.6 teslas. The diameter of the loop is 8 centimeters, so the radius is 4 centimeters or 0.004 meters, and we divide that by the change in time, which is 0.3 seconds. That gives us an induced electric potential of 0.0268 volts. So there's the potential. Our next step is to find the current, because that's what the problem asked for. So we'll use Ohm's law that says potential is current times resistance, which means that current is potential over resistance. In this problem, the symbol for potential is epsilon. So current is epsilon over R for resistance. The potential is what we found in the previous step. The resistance is 4,800 ohms. So we get a current of 5.59 times 10 to the minus 6 amps. So around 6 microamps. That's a pretty small current, and I guess you probably can't even feel that at all when you're in an MRI machine. So the current induced is actually pretty tiny, nothing to worry about.